right, we're at the end. It's been a long course. I will make this short because I know you're really busy. These are more the fun labs. There's not a lot of coding. Hopefully, a lot less issues with these labs. I just want to give you a brief overview of what the labs are using, like what is the technical underpinnings of what you're using, and then just have you go off and do them. So we're going to talk about data warehousing, and then I'm going to also talk a little bit about data notebooks. So in terms of data warehousing, the thing that you'll be using is BigQuery. On AWS, they have multiple styles of data warehouses. They have Redshift, which is similar to BigQuery, and then Athena, which is layered on top of S3. And we'll talk about the differences between what these systems do in a bit. Azure has their data lakes, and this is the name for warehousing in general, like, or they're synonymous with a warehouse is a data lake. And then an open source version called Hive, if you want to roll your own. Okay, so the motivation for a data warehouse is that you have a lot of applications that have a massive amount of data, and you want to be able to query them very quickly. And up until data warehouses, you were stuck with very few options. So you had these small transactional, typically in-memory databases if you wanted performance. And these things would allow you to do a bunch of querying really quickly, but they're limited in capacity. For example, if you have to be in memory, all of a sudden that's the size of the database. Your working set size has to fit all in memory, so they're not going to scale to a massive amount of data. You could also have large file systems. So you could store all your data in cloud storage or S3, and then when you want to do stuff like query that data, you can write a bunch of scripts or do a bunch of grepping and then see how far that gets you. And this was me circa 1990 something to crunch on the data, all the data that I had. I had a bunch of network packet traces, and I had them all in a file system, and I was sitting there scanning all the packets to get the data, and I only needed like a tiny bit of data. And I have the example of what I was doing in the next slide. So that is great. You can store a gazillion things. I mean, you got terabytes of disk space. Yeah, you could store it there, but then if you want to query the darn thing, you're stuck, right? Like you have to scan all of that data. Finally, we have the NoSQL databases, which we talked about earlier. These do store massive data sets. And as it turns out, the technology underneath these things, the scalable ones, is basically a distributed hash table. Like you get some key, you take a hash of it, and that determines where to go retrieve it from. And so you can get, every time you add more nodes to this hash table, to serve this hash table, you get scalability really easily. You can store a bunch of stuff, but then try querying the documents in that NoSQL database. If that's the way you're storing, is to take a hash and that identifies your location, well then if I need a certain subsection of my items, I want to search on all the users with the first letter W, then I'm stuck. Then I have to like go and hash every single user or hash every potential key and then retrieve it. Okay, so and you saw in your apps, you have very simple gets and puts into the cloud data store. And then if you actually want to do a search, you're going to have to like scan the whole thing, right, which is an operation. There's some limited querying, but it's not the kind of querying that you would expect to have in a real database. Okay, so data warehouses, these are things that are typically used for what they call online analytical processing workloads. And typically you can think of these things as log processing for analytics. So when we saw this show up in Super Mario Run, they are logging everything that a user does in that game in order for them to improve the user experience, right? So how are you going to store all that data so that you can then do analytics on top of it? And this is where the data science comes in. I have a bunch of data, but I need to, in order to create actionable information on it, I have to be able to query it very efficiently to generate the data products I'm interested in. And we'll see when we talk about the data science, the notebooks that data scientists are using, you'll see that a lot of them will point themselves to a data warehouse in order to get the data, in order to generate the visualizations that you can then present to people to action on. So these data sets typically have the property of what they refer to as worm. So write once, so you're never modifying the things. You're always, it's like an append-only storage, and then you'll eventually read or query it a bunch of times. So if you have this kind of workload, then you can optimize your data backend to support just that. And this is why you see all of these data backends. It's like, each one is doing a very specific thing. And so you have to choose the backend that suits your application. And so if you have this kind of worm workload, you would do a warehouse. Okay? And then specifically, if you have a large amount of data that you're storing, well then your backend has to support large writes. And if you're querying it a lot, then it has to be able to support large reads and parallel reads. Okay, and these warehouse applications specifically don't require transactional properties. So when we talk about traditional SQL databases, that was their thing, right? Like for financial transactions, you have to get transactional consistency. These workloads, as soon as you write something, that's it. It's archival. So there is no transaction that you have to support in these things. So you don't need the SQL, you don't need the spanner. Spanner will scale and support SQL, but you don't need those semantics. You don't need that consistency that those databases, those data backends support. And so these things are typically implemented using cheap disks and slow CPUs is the idea for a data warehouse. So we're going to talk about BigQuery. And I think this is sort of the system that kicked off, at least commercially, what kicked off this whole thing. This is definitely a differentiator. When people talk about why they chose Google Cloud, because most of the cloud providers have something similar now, but initially it was BigQuery implementing this workload that got a lot of people attached to them. And so now it's machine learning, but another one was BigQuery. Okay, so BigQuery is a fully managed no-ops data warehouse. And so this means it's serverless, right? So it's just like S3. I give you the tables to store, and then when I want to actually access it, you'll spin up enough servers for me to be able to process what I'm sending you. And then you will do all the replication. So like S3, you only get a handle to the object you want, and then if a bunch of people are accessing it all over the world, it will replicate it for you, and it'll spin up a server to serve those objects. Same idea is happening for BigQuery, and the replication of these tables is being done underneath that's transparent to you. And then if you are kicking off hundreds of queries against your data set, it'll do the replication, and it'll also spin up the server resources required for you to then get that querying throughput. So just like the previous serverless stuff that we talked about, this is basically a serverless data warehouse. And so it's been architected. You can insert 100,000 rows per second and hundreds of terabytes per second because of the way it's been architected for this application. And then it will, after you ingest all of that stuff, it's ingested in a very particular way to then allow really fast querying. And that's where the high-performance querying via a SQL-like interface comes in. It's not running like a traditional SQL underneath, but it's allowing you to interact with it using the SQL language. Okay. And one of the things that they talk about is that this allows you, rather than taking the data and bringing it to your code for processing, you can actually now bring your code into the cloud and then use BigQuery queries to process it in a backend directly. Okay, so how did they do this? Like, what is the secret sauce? To motivate how it's architected, I'm going to go back to what I did when I was a graduate student. Was if I had a bunch of data, like a network traffic trace to store, I would just store it in a log file. And you did this in your network lab, I believe, when you did a TCP dump and you captured a packet trace. That packet trace is sitting there in a single file. And it's stored in your file system, a TCP dump trace, for example. And so if you recall, you have something like this. So it'll be stored in a binary format, but it's still stored linearly in that format where you get a packet at a time. Every row is a new packet. So for this, if I wanted to, and this is what I was doing, I was calculating inter-arrival times of packets. I wanted to get the distribution of packet arrival times across the entire trace. And if this thing is stored like it is as a flat file, I have to read the entire trace. Every single byte of that file has to be read in order for me to calculate inter-packet arrivals, where I'm only interested in the very first field of that row. Okay, so that's the problem. And this is a common access pattern for data analytics. If you're interested in the behavior, user behavior, like what is the inter-click time of users, you don't want to download everybody's click history, right? You don't want to, all the fields that are collected, you don't want to have to access all those fields. You're very specifically interested in inter-click time. You only need one piece of that entry for every thing that you do. So idea number one for BigQuery was to do column-oriented storage. So what is this? The idea here is to split that trace into columns and store those columns in separate files. So these are all of these things are contiguously stored in a single file, and then you have a file per column. And this basically reduces the data access for column-oriented queries. So back in this example, I would have a column here as the packet arrival times. And when I wanted to do this inter-arrival time of packets, I would only have a single file to access, and it would be 1/nth of the total data size of the file on disk. So is that clear what it's doing? So that's one benefit. Now I have a single file, and everything that I'm reading from the disk is going to be consumed by the thing I'm interested in. I don't touch anything, any of the other column, any of the other pieces of data in that column. Okay, so that's the first thing. The other thing this does is that you can get much better compression. So if some of you are taking the multimedia class, when they're talking about compression, it's much easier to compress something if all the data is very similar. So if I took a column of this, it turns out if you take one of these columns and you zipped it up, gzipped it, you would get 97% compression. Because if you look at this, like it's got a lot of common, in fact, it's only using digits and the semicolon and the period. So that is something you can really squash down very, very finely. And this is where the benefits of using a data warehouse come in. Because if I can store on the back end something super compressed, I can actually ingest a ton more data in my storage. So the column-oriented storage is a big thing. It reduces the access, the amount of data accessed, and it gives you better storage compression. And then what they do is they replicate all of these files on the back end. So if I'm only interested in inter-arrival times of packets, that's the only thing that gets replicated. If, for example, I would never care about like these fields, like the ACK, the sequence number, the advertised window size, I could care less about that data. And that data, because I'm not accessing it in my queries, would never get replicated. The only thing that would get replicated were the things that were showing up in my querying. So that's another advantage of this. Okay, the other part of it is to employ serverless querying. You don't want to have to worry about the resources being used. Well, I mean, you worry about it in that you have to pay for it, but you don't have to worry about it in that you have to actually instantiate them explicitly to handle the workload. What you want to do is be able to spin up the resources you need to answer that query as quickly as possible. And BigQuery at the time, this is from last year, I don't know if this is still updated, it will allow you to spin up up to 2,000 nodes to process your workload. And then if you are querying at this rate, it will underneath start to replicate the data that's involved with your querying. And this is what the sharding is talking about. And then they can do this because on the back end, you got this petabit network that's able to push data sets and replicate them on the back end very quickly in order to handle your workload. And then the idea is if it's completely serverless, you're just paying per query. And you're reducing the cost to actually do the storage if you've compressed it enough. Okay, so this is where BigQuery is really helping in terms of performance and applications. So what I'm going to show you now is just a demo of the UI. And I show you this demo because there's some things in the UI that I want you to see before I go through it. So I'm going to run these queries, and one of the things about these queries is that it's using the public data sets in BigQuery. One of the things that Google wants to do is be the sort of the fountain of all the data sets, or the storage medium of all the data sets, so that people can then use BigQuery to run whatever they want on there, and then that's how they monetize the data. So Google is all about monetizing the data that they have. This is just an example. So this is a data set, the names of babies in the US from 1910 to 2013. And then this one is a Wikipedia data set that you can use to query. So I'll just show you some examples of doing this. And some things that I want you to pay attention to make sure that you keep your costs low, which is helpful. So if you go to BigQuery, there's a query editor that you can run, which is shown here. And if you copy and paste that query in there, you'll see that there's an exclamation point on this saying, hey, there's some syntax problems here. It turns out this syntax is standard SQL, specifying that data set. Legacy SQL. It specifies that data set, but this thing is using by default standard SQL. So if you get this exclamation point on any of the queries that you see, what I want you to do is to go into the query settings, and this UI supports, or the BigQuery supports both legacy and standard SQL dialects. And so you're just gonna, for this particular query, you're gonna switch it over to legacy and then redo this query. The other thing is when you cut and paste a query into this UI, it will give you an estimate of the amount of data that is going to be accessed in the query so that you can estimate your costs. So BigQuery does charge you by the amount of data that you query. And so 100 megabytes is pretty cheap. So you can run this query and it'll be like a penny, under a penny. And then it will emit the results, which will be down here. Okay, so those are the results. Let's see here. I'll go to the next one. I want to show you what happens in the, to always pay attention to this estimate over here on the right. If you copy and paste a query that is going to take a huge amount of data, you should know to always check there. So here's one that costs a lot more. So this is 4 terabytes. And so if you see something that will require something like that, you should be well aware of the pricing for this thing. It's not as bad as AutoML as someone found out, but it's still, if you look at the pricing for this, it's $5 per terabyte. So if I would have hit run on that particular query, that would have cost me $20. Nope. So I think this is still up to date. I think that's the chart, or maybe this is last year, but it's a lot, right? Like there goes half your coupon. So always pay attention to that. And here's the thing: this happens in the UI. The UI shows you that. If you're doing this from the command line, that's where it's a problem because you don't get the estimate from the command line querying. And this is where you can really rack up charges for this. Okay. So maybe this is better that these things will happen next week, hopefully, like after people are done with their final project, so that they don't, well, actually, you need to keep your final project up for grading. But if you accidentally run your coupon down, I'm still issuing coupons. I still have some to give out, so yeah. Okay, I wanted to point your attention, if you want to play around with BigQuery, to all the data sets that they have. One of the ones that I like is this QuickDraw with Google. So this app allowed you to draw a stick figure, and then Google would try and guess as quickly as it could what it was you were drawing. And so all of the data for people actually trying to draw certain objects are actually stored as a BigQuery data set, if you're interested in it. The GitHub, the history of commits on GitHub is also there, and this is what your code lab will have you work with, is to do some analytics on the GitHub data set. The New York City public transportation data set. So if you look at any of the so Google has a quest, a data science quest. If you like this kind of stuff, you can actually go and do some of their code labs, and they'll point you to the city data that they have hosted for you to do some analysis on that data set. So like taxi arrivals, phone calls to 411, all of these pieces of data are there for you. There is ship data from 1662. So one of the interesting things that they show in one of the code labs is finding the ships that were nearby when the Titanic sank in whatever it was, in the early 1900s. And then I have you do this as part of your initial step in one of the labs, is just to look at I have you look at the Bitcoin blockchain, because that thing is completely stored on BigQuery. And if you do have a query, so the blockchain isn't queryable as easily as a regular database. And so what a lot of these companies are doing is building indices on top of the blockchain data so that you can then do some efficient querying on top of all the transactions that are going on underneath. And so this is an example of doing that, that it's been imported into BigQuery, and now you can run BigQuery queries against that data set. Okay. The next thing you're going to do is run and test out a bunch of data notebooks. The hosted service is Datalab. Azure's got their notebook service. Typically, if you don't want to use a cloud instance, you could run these things locally with IPython and Jupyter. Well, mostly Jupyter now, because IPython got replaced by it. So what are data notebooks? These are basically interactive authoring tools. You can think of having a Google Doc, being able to cut and paste code into like boxes in Google Docs, and then being able to run a Python interpreter against that code and have it produce a visual result. That's effectively what a data notebook is. It's like a Google Doc augmented with a Python interpreter. And this is the de facto way of sharing scientific results, where you want to have these scientific results be reproducible, right? Like if you have a data set and you've generated some products, visual products for the paper that you published, you want people to be able, with that same data, to produce the same artifacts as you have generated in the paper. And data notebooks are typically one of the ways for doing so. So it was initially IPython, this interactive Python, and now it's Jupyter, and these are server-based notebooks where the Python interpreter is sitting there running on the server, and it's being wrapped in HTML so that when you hit the server, you get basically an interactive Python. Is that me? No, it's not me. You have an interactive Python interpreter on the server, and that interpreter is running basically a notebook, the authoring tool, and then it has different places inside of the HTML for you to cut and paste Python code into, and then run the code directly. One of the things with the server is that if your notebook requires certain Python packages in order to produce the data sets that you have, you would have to install all of those packages on the server running your Jupyter instance. And that's what you'll be doing. Okay. So you can do this locally. It's really simple. You create an environment, activate it, and then install Jupyter, and then run the Jupyter notebook. And much like in the Cloud Shell, when you run it, it brings it up on a local port. The same thing with Jupyter notebooks. Once you run the notebook, it listens on port 8081, and then you connect up with it via your web browser, and then you have the full data notebook experience as you would if it were hosted by someone else. Okay, so that's basically how you run it. The other thing that people are using alongside of Jupyter is this thing called Binder. And the idea of Binder is to combine GitHub with Docker with your interactive notebook. And this is a full end-to-end solution for reproducing results. So the idea of Binder is that in your GitHub repository, you have the GitHub repo contain the notebook, all of the package dependencies for the software that you need to run that notebook. And then what you do is send it to Binder, and Binder is automatically going to build the Docker container that has both your data and your code and all your packages in it, and then pop up a Jupyter notebook with all of that stuff loaded so that you can then reproduce someone's results. And so this is really powerful because then it's like I just do a one-click thing on Binder, and then I get your notebook as you were using it in your experiments to produce that paper. So it's very similar to what we're trying to do here, combining the best ideas of Docker and then applying it to basically Jupyter. So here's an example of, this is the 2017 Nobel Prize in Physics. They released a notebook, a Jupyter notebook, to allow people to take the data that they got from the collider and then to run some of the same experiments, the processing experiments, to produce the graphs that were in that paper. So this is just something that everybody the scientists are moving towards. And this is what you would do as a data scientist if you were trying to publish a paper. You would publish your data notebook and hopefully a binder that shows the software that you use to produce it. Okay, so we're going to use Google Cloud Datalab, and this is basically a hosted Jupyter instance. There's not much to Cloud Datalab. It's basically going to launch you a VM with the Jupyter software packaged up and run automatically for you. You could have easily done this using a couple clicks and a couple commands on the VM, but this thing is just doing it. It's just wrapping all of that stuff up to you for you, and that's what the labs will be. Okay, so with that, I'm going to go through a couple of the labs, but I think I actually just want you to. Actually, you know what? I'm gonna skip going through the labs. I'm just gonna have you just do your final project actually, and any of the labs, unless there are any questions. I think I'll just let you work uninterrupted rather than me talking more at you, because I think you've probably had enough of that this quarter. So, all right, I'm gonna stop here.